All right, so welcome back to Math 341 Probability, Stat 341. Let's agree to allow the meeting to be recorded. And so what we're going to do today is, this is lecture 4. This is going to be the first of the completely flipped classes. So you were supposed to watch the video beforehand. If there are things that you wanted to talk about, you were supposed to either email me or just mention it right now, and I'm happy to do that. If not, we will just deal with your other things that you may find interesting or want to talk about. And again, the purpose of this is to give you 3 different classes, during the start of the semester, so you can get a sense of what you might want to do structurally going forward. Just because we start doing something doesn't mean we have to continue doing it that way, but this just gives us a chance to try to think, what is the most efficient way to use class time that we have? So a lot of the lecture is related to highly theoretical material that for the most part we don't really need unless we're going to become pure mathematicians interested in the absolute fundamentals of probability theory. So in terms of choosing a lecture to flip, this is a really good one. If you want to do probability rigorously, you really have to decide what objects are you discussing. What is the space in which things live? Which events do we assign probabilities to? Not every event has a probability assigned to it. And then once we have these events, how do we actually choose what the probabilities are? And so, this leads to the Kolmogorov axioms of probability. And then you're looking at various consequences. Some of the consequences are very straightforward. If I have 2 events, A and complement of A, then if I know the probability A happens, the probability A doesn't happen is just 1 minus that. And this is going back to what we were talking about beforehand, the opposite episode from Seinfeld. If people want to have a Seinfeld party, let me know. Happy to watch that episode again. It's an outstanding, brilliant episode. Has applications in modern encryption and error detecting, error correcting codes. I kid you not. All right. So we have all of that stuff. Does anybody want to talk about any of that theoretical base work? For the most part, when you're doing probability, in a first class, it's I'll know it when I see it. If I want to talk about events, my events are going to be the probability I live in an interval, the probability I live in a rectangle, the probability I live in a triangle, the probability I live in a cube, the probability I take on a discrete set of integer values. These are the things we are talking about. We are usually not talking about the probability that I choose a number and none of its digits are 7. Or at most, 3/5 of the numbers of digits are 7 up to this point. We're not really talking about strange events like this. And these really aren't that strange. There's much worse things you can talk about. Now, you must be careful. There is a wonderful result called the Banach Paradox. If you are looking for an ambitious senior colloquium, this is it. It basically says if you take a solid sphere, you can cut it into 5 disjoint pieces and move 3 pieces in one direction and 2 pieces in another. If you translate a piece, does it change its volume? No. That's an assumption. That's a very reasonable assumption that I think we're all willing to accept, that as you move an object in space, its volume doesn't change. If I rotate it, does its volume change? No. If I had my daughter here, I'd actually be physically rotating her and whatnot right now. We do that when we actually teach people how to do Rubik's Cubes. So if I move by translation and rotation, I should not change the volume. So if I move 3 pieces over here and 2 pieces over here, what's the sum of their volumes? Yeah, this is the volume of the initial sphere. But you can actually rotate and translate 3 of these pieces and put them together and get an exact copy of the original unit sphere with nothing missing. And you can do that with the other 2 pieces and have nothing missing. So what should we make our sphere out of? Well, what do we want to make the sphere out of? Money, gold, something like that. You've now doubled how much gold you have. Lather, rinse, repeat, shampoo mathematics. Keep doing this, and you can make as much money as you want. Does this, the fact that you can make as much money as you want should not bother you. The fact that mathematically we can do something like this should bother you. It relies on something called the uncountable axiom of choice. And the sets that we need to do, these cuts, cannot be described. So we're not going to be able to do them with a knife. These are strange mathematical sets. You're looking at equivalence classes, your modulo the rational numbers and taking a representative of each one. We are not going to assign probabilities to stuff like that. So this is really the high level of what was going on in the book and what was going on in that lecture. Is we have to be careful because of stuff like this. I believe we talked about Russell's paradox, where you can have the set of all things. And so this is just showing us that we have to be careful in a class like probability in terms of what we talk about. And so now you can just check off the box, okay, yes, professor warned me we need to be careful, and now we'll just proceed without ever worrying about it again, right? And we'll just now calculate probabilities of events. Okay, so is there anything people want to talk about in greater detail about axioms of probabilities or consequences? Okay, so then what I want to do is I want to use the rest of the time to just really emphasize ways to think about problems and ways to attack things. And again, if there are problems from the book that you want to do, I'm happy to do a couple of problems from the book. Or if there's just general probability problems, happy to do that, or general coding problems, happy to do that. This is our chance to use class time really effectively. And again, this is the perfect topic to push to the reading or watching at home. It's not something we're going to do much with, but it's something that has to be discussed. So what I want to talk about is sniffing out equations. Right. Is there anybody who, we have an opening for supreme deity of the universe? Anybody interested in the job? Excellent. Hopefully you will not be vengeful and you will be compassionate to the mathematicians, statisticians in your universe. Okay. If you could, what would you make the derivative of a product? You would make it the product of the derivatives. Thank you. Right? Wouldn't that have been a wonderful universe to create? Now, of course, we have the Leibniz school that this is the best of all possible universes. Therefore, there must be some goodness over the fact that this is not the way things are. So do people remember the product rule? If your life depended on it, could you prove the product rule right now? Okay. How would you prove the product? Okay. So we will say, let's let A of x be f of x, g of x. So it's always good to start with the definition of the limit as h goes to 0 of a of x plus h minus a of x over h. Now what do we do? Okay, so we have f of x plus h, g of x plus h minus f of x, g of x over h. Now what? So we add 0. And so this is the same as the limit as h goes to 0 of f of x plus h, g of x plus h, minus, plus, minus. Now, we want to subtract off f of x, g of x plus h. I mean, you can do it the other way, but then you would be writing your answer in reverse form of everyone else, and we would just laugh at you. I mean, could you say the derivative of the product is fg prime plus f prime g? Absolutely. And so now, with a little bit of work on limits, this is going to be the same as the limit as h goes to 0, f of x plus h minus f of x over h times the limit as h goes to 0 of g of x plus h. And then we would have plus f of x, because that doesn't depend on h, I can just take it out, limit as h goes to 0 of g of x plus h minus g of x over h. And I'm just using a bunch of limit rules. The limit of a product is the product of the limits. The limit of a sum difference is the sum difference of the limits. And now the first piece, just becomes f prime of x. The next piece is just g of x plus f of x, g prime of x. And so the proof isn't that bad, and we use one of the most useful concepts in all of mathematics, do nothing, which again fits well with a lot of Seinfeld episodes. I would probably do the sales pitch where they are pitching the show to the network of a show about nothing. Why would people watch it? It's on TV, not yet. All right. What if you didn't know the product? What if you had to experimentally discover it? And again, in a class like probability and statistics, where we will be gathering data and trying to experimentally discover things, it's not bad talking about how you would experimentally discover something like the product rule. So I got a call yesterday from one of my nieces. She is around 4th grade. And you're always worried, is everything okay? She needed a definition of what is a mathematician. And so you're happy to help her. What definition do you give to your 4th grader? And I basically said, here's the long technical definition, here's the short one. We solve problems using things like numbers and equations. You can do more than just numbers and equations. You gather data and analyze. And so how might you try to sniff out the product rule? So I need functions f and g such that we know f prime, g prime, and a prime with a equals f times g. So I need to find functions f and g such that I know the derivative of f, I know the derivative of g, and I know the derivative of their product. So can anybody give me functions? Yes.
Fx squared.
Okay, f of x is x squared.
Like you take the x, like multiply.
You have to tell me f and g.
Okay, f is f of x and g is f. Yeah.
So I have the square of f of x.
Yeah.
What's the derivative of the square of f of x?
2 f of x. The derivative of f.
So it's 2 f of x f prime of x. Why? That's using the power rule. Right? Now, the power rule is a special case of the product rule. So you might be able to prove that independently. It's also a special case of the chain rule. You can prove that. You've got to be very careful not to do circular arguments. And so I will put a little circle down here as a warning, and we'll talk about that in a little bit.
So I guess this is
Okay, so f of x equals x and g of x equals.
maybe g of x equals 9.
Okay, so then you would need to know the derivative of x sine of x. Do you know the derivative of x sine x?
Oh, no.
I need to know the derivative of f, g, and f times g.
Say f of x is x, say g of x is x squared.
Good. More generally, we know the derivative of x to the n for any n. So we know the derivative of x to the r is rx to the r minus 1 if r is a real number. And so let's try the more general thing. Let's say f of x equals x to the n, g of x equals x to the m, and then a of x is f of x, g of x is x to the n plus n. So this is just a little bit more general than your suggestion. Your suggestion of x and x squared is fine, but the argument and the analysis is so similar, I might as well do this whole large class simultaneously. We know f prime of x is just n x to the n minus 1, g prime of x is m x to the m minus 1, a prime of x is n plus m x to the n plus m minus 1. So I want to look at and see, is there any combination of f, g, f prime, and g prime that will give me a prime? And again, I don't know for sure that the product rule will only involve f, g, f prime, and g prime, but it seems reasonable. What would be a really simple case to take for g? We're trying to sniff out the product rule. What might be an interesting choice to take for g of x? Nope. There's a really nice choice with g of x where if I take g of x to be this, I know the derivative of a of x with respect to f of x. 1. So if I take g of x equals 1, I know f prime comes into play. And if I take f of x equals 1, I know g prime comes into play. So we know we need an f prime of x and a g prime of x from taking g of x equals 1 and f of x equals 1.
Those two are being multiplied together because the f prime of 1, or the derivative of 1 is 0. So it can't be.
Oh, good. So now, because if we take g of x equals 1, we would have some kind of piece like f of x times g prime of 1. I'm sorry.
Yeah.
And so if g prime comes in, so maybe we have something like f prime of g of x.
Yeah.
So maybe this is suggesting something like f prime of x times g of x plus f of x g prime of x from this analysis. Because if we take g of x equals 1, g prime vanishes and we get f prime, which works. If we take f of x equals 1, then this piece vanishes and we get g prime. So look at this. Before we do any detailed calculations, we've already got the suggestion that it's f prime g plus f g prime. As a candidate, there could be other things that work, but this is the simplest rule possible. So, sometimes, things that look painful might actually be good for us, and it might be a good thing to go through. So there might have been a reason why the deity has chosen the product rule to be this. It's not the worst possible product rule possible. If you're thinking about things, this is actually the most natural thing you could think of from looking at special cases. And now if we look at what we have f of x, f prime of x, g of x, g prime of x. A formula like this is suggesting that all of them should come into play. And now if I look at stuff like this, how could I get an n plus m x to the n plus m minus 1? Ooh, f prime times g plus f g prime, they're all going to have the same power of x. If I did things like f of x squared or f of x times f prime of x, the powers of n are going to be crazy. And this is the advantage of looking at x to the n and x to the m rather than say x and x squared. Because if you look at x and x squared, they're so small, there might be many ways to put them together. I could take the limit as n goes to a billion, a trillion, quadrillion, and then keep n so small that it seems absurd that I would have a formula that would keep working. And so when we put things in, check, f prime g plus f g prime is for us going to be n x to the n minus 1, x to the m plus m x. The correct order would be x to the n m x to the m minus 1, which is n plus m x to the n plus m minus 1. So it works. Have we proven? No. Have I given this class the 16/64 question yet? So just because we've done a case doesn't mean we've done a proof. So the question is, are there any other functions where we know, f, g, and a equals f, g, and we also know f prime, g prime, and a prime. So polynomials were very nice. There is one other function I can think of. Let's take f of x equals sine of x, g of x equals cosine of x, and a of x equals sine of x cosine of x. Okay. What's the derivative of sine? cosine. What's the derivative of cosine? Right. And the way I like to remember that is when you're doing derivatives, you have to remember where to put the minus sign. It goes with the sign. And if you think about what's going on when you go around the unit circle, cosine starts off at 1 when x is 0, or when the angle is 0, and then cosine is decreasing. So the derivative of cosine should be negative from looking at the unit circle. Okay, well, when I look at this, and you look at a of x, how do I know what the derivative of a of x is? You know, I would need to use the product rule, it seems. And if I'm using the product rule, well, then I would have to know the product rule. So I probably have chosen this for a reason. Does anybody know what sine of x times cosine of x is? It is 1/2 sine 2x. And so if you remember your trig identities, then a prime of x is going to be 1/2 derivative of sine is cosine 2x, and then derivative of cosine 2x, the derivative of 2x is 2, so it's just going to be cosine of 2x. So we are using the multiple rule. The derivative of f of cx is c times f prime of cx. So you would need to know that before going to the product, but that's an easier thing to prove. What that's basically saying is if you speed up time by a factor of 3, your speed is going by a factor of 3. Okay, so now let's check. What is f prime g plus fg prime? That's going to be cosine x plus sine x negative sine of x. So that's cosine squared x minus sine squared x. What's a prime of x? Derivative of cosine 2x is, oh, sorry, we've already got it. It's just cosine 2x. So does a prime equal f prime g plus f prime g? You know, one of them is cosine squared minus sine squared. The other one is cosine 2x. I'm sorry?
Yeah.
Yeah, if you remember your trig identities, you know, cosine of 2x is just cosine x minus sine x sine x. So they are the same. So this is a more interesting example of you trying to prove the formula. And again, I really don't care about proving the product rule. You know, this is something that we know. The proof isn't too bad. I care about the method. I care about the mindset. How do you take data? How do you collect data? And once you have that data, how do you act with it? So the reason I wanted to just warn you about some things is, let's say I give you the limit as x goes to infinity of x over e to the x. Does anybody remember how you would handle that? L'Hopital. You know you've made it when your name is a verb. Yeah, when you can say, you know, Miller something. Oh. Right. So you take the derivative, you would get the limit as x goes to infinity of 1 over e to the x. That's just 0. What about the limit as x goes to infinity of x over cosine of x? Sorry?
Well, I mean,
Yeah, cosine is going positive and negative. We don't have infinity over infinity or 0 and 0. Not L'Hopital. L'Hopital. Lopable, I like lopable. Lopable. Right. What if I gave you the limit as x goes to infinity, let's say x goes to 0 of sine of x over x? What would that be? Okay, why would it be 1? Okay, so we take the derivative of each, we get the limit as x goes to 0 of derivative sine is cosine of x over 1. Yeah. Well, if you use the Taylor series expansion, your sine of x near 0 is x minus x cubed over 3 factorial. So sine of x is approximately x. So the ratio is going to be approximately 1. So why am I writing no here? The reason is you're using L'Hopital's rule. What do you need to know for L'Hopital's rule? You need to know the derivatives. How do you calculate the derivative of sine of x? Sine prime of 0 is the limit as h goes to 0 of sine of 0 plus h minus the sine of 0 over h. What's the sine of 0? So this is just the sine of h over h. That's exactly the same limit as before. So if we're going to use L'Hopital's to calculate this, we need to know that this limit is 1. Because if we don't know that this limit is 1, we can't use L'Hopital because we don't know what the derivative of sine is. So this is just a warning to be very careful that you don't have circular arguments. If I want to use something, I need to make sure I know all the conditions. Okay. Any questions on any of this? So the question is, how do we calculate this limit? So I mean, this is a really good question. I do have, I think, drawing functions here. I insert like a shape. Probably. Wait. Okay. Shapes. Okay, so it looks like I can insert shape. So I'll try if I can do very quickly a shape. Unfortunately, it's a filled-in shape, but oh well. All right. So I have a nice filled-in circle. And what I can do is I can construct regular n-gons. And so here would be a square. And then I could circumscribe things as well. And if I inscribe things and I circumscribe things, I can basically sandwich quantities such as pi between them. And then it's actually best to work with powers of 2 and just you keep subdividing each side. And so I would go from now the square to the octagon. And then for each one of these, you can calculate the perimeters and the areas. And then you can use this to get, sine by doing something like this. So I'm not going to go through and do the details now. If anybody wants to, I'm actually happy to do that. And there's some beautiful formulas for pi that you can get from this. But it comes from, a sequence of approximation. The inscribed stuff comes out, the circumscribed stuff comes in. It's much better to work with areas than to work with perimeters. This is a real thing from calculus. If you've done 150, 151, and they've talked about curves, it's very hard to find lengths of curves. You've got this ds is the square root of dx squared plus dy squared. It's a pain in the ass, the technical term. But if you're working with areas, it's much easier to just do those integrations. And so you would much rather work with areas rather than. Did I give you a homework problem about dividing, like 1 divided by 99899? Did anybody do that? Yeah. Let me see if I can stop the share, toggle. Okay. What was it, 99?
Is 998.
Oh, there's 119. Okay, thank you. Okay, and then let's multiply it by few zeros maybe. Here we go. So it's 0.0010010010020050080130021034034055089. Does this look familiar to anybody? Sorry? What is this? It's the Fibonacci. Do you think it's always going to be the Fibonacci's? Why not? Yeah, eventually the Fibonacci numbers have too many digits. So we know when we're looking at this pattern that this miracle is going to stop eventually. So if we go just a little bit further, 89, 144, 233, 377, 610, 988, and no, 988. And now we're starting to have some issues. So I always love it when you can see the train wreck coming. I was helping out my son's team in baseball, and they needed runners a few nights ago for fielding practice. And so I was running from second to third. My son was alternating with the other first baseman, and he could see the path of the first baseman through to get me at third, and he could just see that it was going to intersect me, and he's just admiring, the physics of what's going to happen. And you just know that it's coming. So we know when we're looking at this that the miracle can't continue. How much time do you think I spent going through fractions before I found this? So do you think there's something deep going on behind this? Yes. This is not going to be an accident. And so what I'm going to do is I'm going to take a quick screenshot of this. And stop the share and go back to the other. Oops, sadly went back to what I was just at. Okay. And so I will paste it in here. And so what I want to do is, this is the bonus lecture, is I want to do a little bit of material right now that we're not going to need until later in the semester. It is one of the most brilliant ideas in mathematics. It's called generating series. We take a bunch of local data and we create this global object. And somehow, if we're lucky, this global object is easy to analyze, and then we can frequently use it to get information about other problems, or sometimes even about the local data. Anybody know what the most important essential result of this course is going to be? What are we leading up to? What's the big thing that you have to know at the end of probability? Central limit theorem. The name is a really good indicator. One of the ways we will prove this in general is using generating functions. So all right, so we are going to have a generating function. Can somebody give me a definition of the Fibonacci's? Okay, so I'm going to just tweak it ever so slightly. So, well, there's several different definitions. So each number is the sum of the previous two. It was just a text from my son. I was dropping him off after taking him to Pittsburgh for a doctor's appointment. Just try to get everything done beforehand. And as we were driving, there was a car that had a grill fall off and almost hit us. It's been an interesting morning. So, all right. So these are the Fibonacci numbers. Is there any mystery to the Fibonacci's once I give you this? So if it starts 0, 1, 1, what's next? Next. If I told you your grade in the course depended on you using paper and pencil to calculate the 1000 Fibonacci number that you gain. You get it right, you get an A plus in the class, you get it wrong, you get a 0. Paper and pencil per 1000. Do you have any idea of how big the 1000 Fibonacci is?
It's going to be enormous, but if we haven't measured the idea, I feel pretty confident.
Okay, what if it was 10,000? So here is 1,000. 1,000, yeah, 1,000 go for. That's 10,000.
Oh, you're saying- wait, wait.
And here, okay, it's 948. I thought I saw 94895. So it gets a little bit long. Now, when you see something like this, you want to try to put things in perspective. Log. I always forget which way it goes. Okay, so the base goes first, the number goes second. So if I take these numbers and I do the log base 10, that should give me approximately how many digits they are. If I do that, the first one is 208 digits. The second one is around 2,089 digits. The next one is 20,898 digits. Do you think you could get 20,898 without making one mistake?
Unlikely.
We've got a semester. We can have independent teams. You can keep checking as you go along. No, and this is a serious question. How many days do we have in the semester? Try to calculate. How many calculations are there? Get some sense. Is this something that's doable? You're going to be adding 20,000 digit numbers. How much paper will you need? So I want an estimate. Extra credit. Estimate how painful of a calculation is this? Is this worth doing? Okay.
No.
Well,
I get points now.
No. And again, they give you questions like this on job interviews. Is estimate how many left-handed Yankee fans are there in the United States who smoke, something like this. Can you come up with a nice, reasonable estimate? Well, I know roughly 1 out of 7 people are left-handed. I know roughly the population of New York. We have the Mets, but who really likes to follow the Mets? So what fraction of, I'm sorry, we do have support groups. We have certain number of people who don't follow sports, who don't follow baseball. And can you give me some rough estimate? So for something like this, can you estimate how many pieces of paper would you need? The first couple of numbers in the beginning are so small that you can almost even just throw them away. It's really the stuff at the end that's going to matter. And can you make a rough estimate of just how bad of an assignment this is? Now, in principle, the Fibonacci numbers are easy to calculate once I've given you this formula, because everything is now known. Oops. Everything is known, so in some sense, there's nothing to do. But this is kind of hard to work with. So we're going to define a generating function. We're going to define g of x to be the sum, n goes from 0 to infinity, of fn x to the n. And at first, this seems like a truly crazy thing to do. We don't really know the Fibonacci numbers, so we're going to form an infinite series and work with that. But imagine this has a closed form expression. It turns out this equals, if memory serves, x over 1 minus x squared. Something like that. So imagine we could prove something like that. The hope is if we have this global control, we can understand things. And what you could do is you can then take that and you can then write this as x times 1 over 1 minus alpha x, 1 minus beta x. And then you can write this as x a over 1 minus alpha x plus b over 1 minus beta x. And again, the 1 minus alpha x, 1 minus beta x, I'm just factoring the denominator. So I am operating under the assumption right now that no one wants to see full technical details. You can look at something else later. What I want is I want to highlight the idea. I factored the denominator. What do I then use to get to here? What technique do I use? It is partial fractions. So, your calculus teachers may have been sadistic people, but there was a reason for learning partial fractions. It's actually a very useful technique. Why do I want to do something like this? I can now use the geometric series and expand, and it's x then the sum of alpha to the n Let's make that a little bit lower. Alpha to the n, x to the n, plus a sum of beta to the n, x to the n, and goes from 0 to infinity, and goes from 0 to infinity, by the geometric series. And now we actually have a formula for the Fibonacci number. So we then get Fn is alpha n minus 1 plus beta n minus 1. But I dropped the a's and the b's, so I have to put an a here and a b here. So I'll have an a here and a b here. And we actually have an explicit formula for the Fibonacci's. Now, when you look at this, there's a lot of questions. Can we do this? Do things converge? So, do we have convergence? So we started with g of x is the sum, n goes from 0 to infinity of fn x to the n. So whenever you're doing something, the first thing you always want to ask is, does the object exist? If it doesn't exist, then you can't work with it. Later in the semester, we will be looking at moment-generating functions. What information do you think moment-generating functions give you? I know we haven't covered them yet, but if you had to guess, what do you think the moment-generating function gives you? What concept from probability do you think the moment-generating function gives you? What would you guess the moment-generating function generates? The moments, right? This is not trigonometry where what's 1 over cosine, secant. That always bothers me. To me, cosine and cosecant should go together, sine and secant should go together. Names should be good. The moment-generating function should give you the moments. It turns out the moment-generating function doesn't always exist, and that will complicate some proofs. There's ways around it by using some complex analysis. But a lot of times the moment-generating function exists. So when we have a series like this, the first thing is to make sure it exists. So we need something about the radius of convergence. So in Calc 3, you should have talked about when does a series converge. And so if the coefficients Fn aren't growing too quickly, then as long as x is not too large, high powers of x will be small, and this sum will be okay. So we need a rough bound on the Fibonacci's. Well, we know Fn plus 1 equals Fn plus Fn minus 1, which is less than or equal to twice Fn, as the sequence is non-decreasing. So basically, we get Fn is less than or equal to 2 to the n. Because you don't double each time, you do a little bit less than double. So converges if the absolute value of x is less than 1/2 by comparison with the geometric series. 2x, which is less than 1. Okay, so if we take the geometric series with ratio 2x, everything is going to be fine. So similarly, when I looked at this alpha x and beta of x when I was trying to expand things, as long as x is sufficiently small, then alpha x and beta of x will be less than 1. So everything is going to be fine. And at the end of the day, you end up with Banach's formula. I'm not clicked on the screen yet, thank you. We end up with Banach's formula, which is one of my favorite formulas in all of mathematics. Fn is 1 over root 5, 1 plus root 5 over 2 to the n minus 1 over root 5, 1 minus root 5 over 2 to the n. If I now ask you to calculate the 100,000 millionth Fibonacci number, it's not that bad. Now imagine you're walking down the street and you're beat up by a number, and the police come to investigate, and you try to describe the number. What kind of word might you use to describe Fibonacci number? It's a What kind of number is the Fibonacci's? It's a natural number. Does this look like a natural number? I've got divisions by 2. I've got square roots of 5. Everything cancels perfectly. And this is always an integer. What's nice is 1 plus root 5 over 2 is greater than 1 in absolute value. 1 minus root 5 over 2 is less than 1 in absolute value. So when it is very, very large, this is basically 0. But we know it's an integer. So the Fibonacci is essentially whatever integer is closest to this. So we don't even have to calculate it exactly. We just have to calculate it close enough to know that it is to know which integer it is. So this comes from when we factor the denominator, the 1 minus x squared. And so what I want to just quickly show at the end is just where all this comes from. So we have g of x is the sum, n goes from 0 to infinity of fn x to the n. And so let's look at, and I'm not going to try to do everything perfectly right now. I just want to get close. Fn x to the n. Okay. Has anybody here taken a class in differential equations? If you had taken a class in differential equations, this is a good time to talk about, using series solution approaches to differential equations. You write down a series and you play games with shifting indices. If you are thinking of ever taking a differential equations class, and if you want to do physics, you should, then this is a good way to see this in advance. Well, this is the same as the sum m goes from 0 to infinity f to the m plus 2 x squared. Oh, sorry, x to the m plus 2. I'm just playing an index game. So here, n is equal to m plus 2. Well, this is the same as the sum m goes from 0 to infinity fm plus 1 plus fm x to the m plus 2. Right? And I'm using the Fibonacci relation. And the idea is once I know the Fibonacci relation, I know everything. This is the same as the sum m goes from 0 to infinity of fm plus 1 x to the m plus 2 plus the sum m goes from 0 to infinity of fm x to the m plus 2. So the first one, I pull out an x, and this is the sum m goes from 0 to infinity of fm plus 1 x to the m plus 1. And the second, oh wait, we actually know what that is. That's just x squared times the sum m goes from 0 to infinity of fm x to the m. Well, this is the same as x, and then I could do the sum, say k goes from 1 to infinity of fk x to the k plus x squared g of x. Right? And fk xk, the only thing I'm missing is I'm missing the f0 term. But what's f0? So this is just going to be x g of x plus x squared g of x. And what is this over here? This is just g of x minus x. I don't have the n equals 1 term. So I get g of x minus x equals was x g of x plus x squared g of x. So x g of x. So now we use the bring it over method. So we get 1 minus x squared times g of x equals x. G of x equals x over 1 minus x squared. And now all you have to do is put in the rest of the algebra details and we're done. And it's not even 950. Oh, now just turned 950. Okay. So we got it in just in time. This is the power of generating series. And we will use it later in the semester to understand things in probability. All right, so I'm going to stop.